Welcome to this problem walkthrough. In this session, we'll tackle problem number 1914, cyclically rotating a grid. We'll explore the logic behind handling multi-layered grids, extracting elements, and applying rotations to achieve the desired output. Let's dive in. In this problem, you are given an mxn integer matrix called grid, along with an integer k. The matrix is structured in layers, and your task is to cyclically rotate each of these layers in a clockwise direction exactly k times. Now, what do we mean by layers? A layer is a group of elements in the grid that form a closed loop at a certain depth. For example, the outermost layer includes all the elements in the first row, the last column, the last row, and the first column. The next layer would be the elements forming the next inner rectangle, and so on. When rotating, each layer is rotated independently. A single rotation moves each element of the layer one step clockwise, such as the top left element moving to the top right moving to the bottom right, and so on. If the rotation count is k, it's important to note that k rotations are equivalent to performing k modulo layer underscore length rotations, where layer underscore length is the total number of elements in that layer. The input consists of the 2D grid and the integer k, representing the number of rotations to perform. The output of this problem is a 2D matrix of the same dimensions as the input grid, but with each layer rotated as described. To make this more concrete, let's look at an example. Suppose the input grid is a 2x2 matrix, 40, 10, 30, 20, and k equals 1. The grid has one layer, which consists of the elements 40, 10, 20, 30. After one clockwise rotation, this layer becomes 10, 20, 30, 40. The new grid, after rearranging these elements back into the matrix structure, becomes 10, 20, 40, 30. This shows how the rotation affects the layer and transforms the grid. Expanding on that, the output grid from the previous example is 10, 20, 40, 30. Now let's consider a slightly larger grid for a new example. Imagine the input grid is a 3x3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and k equals 1. This grid has two layers. The outer layer includes the elements 1, 2, 3, 6, 9, 8, 7, 4, while the inner layer consists of just the single element, 5. After one rotation, the outer layer becomes 4, 1, 2, 3, 6, 9, 8, 7, while the inner layer remains unchanged since it contains only one element. The new grid, when reconstructed, will reflect these rotations. To summarize the 3x3 example, the outer layer rotates to 4, 1, 2, 3, 6, 9, 8, 7, and the inner layer remains as 5. When we rearrange these elements into the grid structure, the output becomes 4, 1, 2, 7, 5, 3, 8, 9, 6. Now, let's consider a simpler case, a single column grid. For instance, the input grid is 1, 2, 3, 4, and k equals 2. This grid has only one layer, 1, 2, 3, 4. After two rotations, this layer becomes 3, 4, 1, 2. The output grid, after rearranging, becomes 3, 4, 1, 2. Continuing with the single column example, the grid has one layer, 1, 2, 3, 4. After performing two rotations, the layer transforms into 3, 4, 1, 2. Reorganizing these elements into the grid structure results in the output 3, 4, 1, 2. Now, let's go over the constraints of this problem. The dimensions of the grid are defined as m rows and n columns, where both m and n are at least 1 and at most 50. The total number of elements in the grid, m multiplied by n, can be as large as 10,000. Each element in the grid is an integer, ranging from -1 billion to +1 billion. Finally, the number of rotations, k, is a positive integer that can be as large as 1 billion. Let's look at some edge cases to better understand the problem. First, if the grid contains only a single element, such as 5, with k equal to 10, the grid remains unchanged because there's nothing to rotate. The output would be 5. Next, consider a case where k is large. For example, with the grid 1, 2, 3, 4, and k equal to 7, the layer length is 4. Since 7 modulo 4 equals 3, the grid is rotated 3 times. The output becomes 4, 1, 3, 2. Finally, in the case of a rectangular grid, like 1, 2, 3, 4, 5, 6, and k equal to 2, the rotation will transform the grid into 5, 1, 2, 6, 3, 4. These examples illustrate how the rotation logic applies across different scenarios. To approach the problem of cyclically rotating a grid, we need to carefully consider how to deal with the multiple layers that make up the grid. Essentially, the grid can be thought of as a collection of concentric layers, and our goal is to rotate each layer independently. The first method that comes to mind is the brute force approach. Here, we extract the elements of each layer by traversing the boundaries of the submatrices layer by layer. Once the elements are extracted, we simulate k rotations by shifting the elements one position at a time, and then write the rotated elements back into the grid. While this approach is simple to understand and implement, it becomes computationally expensive for larger grids or when k is very large, as the time complexity involves both extracting and writing the elements, in addition to the repeated rotations. A better alternative is to optimize the rotation process using modular arithmetic. In this method, instead of performing k individual rotations, we compute the effective rotations using k% perimeter of layer. This allows us to perform the rotation in a single step by slicing the extracted elements and rearranging them. This approach significantly reduces the computational overhead and is more efficient for larger grids. Finally, there's the in-place rotation method, which avoids the use of temporary storage altogether by directly rotating the grid elements. While this saves space, it introduces additional complexity in managing indices and ensuring elements aren't overwritten during the process, making it harder to implement correctly. Although the in-place rotation method is space-efficient, its complexity makes it error-prone and challenging to debug, especially for larger grids with multiple layers. Therefore, it is not recommended unless minimizing space usage is a critical requirement. With these considerations in mind, the optimized rotation using modular arithmetic emerges as the best strategy for this problem. The intuition behind this approach is that the grid's layers can be treated as one-dimensional arrays when their perimeters are unwound. Once we have these 1D arrays, we can compute the effective number of rotations required using modular arithmetic, which eliminates redundant rotations and simplifies the process. By rotating these arrays and copying the elements back into their respective layers, we achieve the desired result efficiently. The key observations here are that extracting and reinserting elements can be done layer by layer, and because rotating by the layer's perimeter results in the same configuration, we only need to compute rotations modulo the perimeter. This approach strikes an excellent balance between performance and simplicity, avoiding the pitfalls of brute force inefficiency and the complexity of in-place rotations. The overall steps can be summarized as follows. First, identify the layers in the grid. Then, for each layer, extract its elements into a 1D array. Next, calculate the effective rotations using modular arithmetic, rotate the 1D array accordingly, and finally copy the rotated elements back into the grid. When comparing these approaches, we see clear trade-offs. The brute force method is simple but inefficient for large rotation counts due to its repetitive nature. On the other hand, the in-place method saves space but is difficult to implement and debug, making it less practical for most scenarios. The optimized approach, however, stands out as the most balanced solution. It is efficient, relatively straightforward to implement, and avoids the drawbacks of the other two methods. This makes it the best choice for this problem. From a complexity standpoint, the optimized approach processes each element of the grid a constant number of times, leading to a time complexity of m*n, where m and n are the grid dimensions. The space complexity primarily involves storing the elements of a single layer temporarily, which is proportional to the layer's perimeter. This gives an additional space complexity of perimeter, making the overall space requirement manageable and efficient for most practical cases. In this problem, we are given a 2D grid, or matrix, and our task is to cyclically rotate its layers. Think of the grid as being composed of concentric rectangular layers, starting from the outermost layer and moving inward. Each layer is a closed loop of elements, and we need to rotate these layers by a specified number of steps, denoted as k. For example, if k is 1, rotating the outermost layer means shifting all its elements one position clockwise. Similarly, the same logic applies to the inner layers. Our goal is to take this input grid and return a new grid where each layer has been rotated appropriately. The inputs to our algorithm are a 2D grid of size m by n and the integer k, which specifies the number of rotations. The output will be the modified grid after performing these rotations. Let's now dive into the steps of this algorithm. The first step is to extract the layers from the grid. A layer can be visualized as a closed loop of elements. For instance, the outermost layer consists of the top row, the right column, the bottom row in reverse order, and the left column in reverse order. To handle this, we initialize a list called layers to store the extracted layers. Then, we iterate through each layer using an index I. For the top boundary of the layer, we collect elements from the top left corner to the top right corner of the grid. For the right boundary, we collect elements from the top right corner down to the bottom right corner. Similarly, for the bottom boundary, we collect elements in reverse order from the bottom right corner to the bottom left corner, and for the left boundary, we collect elements in reverse order as well, moving upward. Once a full layer is extracted, we append it to our layers list. After extracting all layers, the next step is to perform the rotation. Once the layers are extracted, we rotate each one. Rotating a layer is essentially a shift operation where elements are moved circularly. For example, rotating by k steps means the last k elements of the layer move to the front, while the remaining elements shift backward. To optimize this, we calculate the effective number of rotations, k_effective, as k modulo the length of the layer. This ensures that we avoid unnecessary rotations when k is larger than the layer size. The rotation itself can be performed using slicing. We take the last k_effective elements of the layer and concatenate them with the rest of the layer. After rotating, we store the updated layers. With the layers rotated, we now need to map these changes back to the grid. After rotating the layers, the next step is to map the rotated elements back into the original grid. For each layer, we replace its top, right, bottom, and left boundaries in the grid with the corresponding elements from the rotated layer. This effectively reconstructs the grid layer by layer. Once all layers are processed, the modified grid is returned as the output. There are a few key insights to note here. First, the distance of a layer from the edge determines its index, with the outermost layer being index 0. Next, instead of performing k individual rotations, we optimize by calculating k modulo the length of the layer, reducing computational effort. Finally, by reconstructing the grid in place, we avoid creating additional grid structures, which helps save memory and improve space efficiency. Let's now look at the data structures and complexity of this approach. The algorithm relies on two main data structures. The grid itself is represented as a 2D list, making it easy to access rows and columns. Additionally, we use a list to store the extracted layers, where each layer is simply a list of integers. Now, looking at the complexity, the time complexity is O(m*n), as we visit each element of the grid exactly once during the extraction and rotation steps. The space complexity is also O(m*n), since we store each element in the layers list. There are also a few edge cases to consider. For example, a single row or single column grid has only one layer, and small grids like 1 by 1 require no rotation. For large values of k, we ensure rotations wrap around correctly using k modulo the layer size. With this understanding of the algorithm, let's see an example to illustrate how everything works. Let's walk through an example. Suppose the input grid is a 4 by 4 matrix, and k is 2. The first step is to extract the layers. Layer 0, which is the outermost loop, includes elements from the top row, right column, bottom row in reverse, and left column in reverse, resulting in 1, 2, 3, 4, 8, 12, 16, 15, 14, 13, 9, 5. Layer 1, the inner loop, contains 6, 7, 11, 10. Next, we rotate these layers by 2 steps. Layer 0 becomes 9, 5, 1, 2, 3, 4, 8, 12, 16, 15, 14, 13, and layer 1 becomes 11, 10, 6, 7. Finally, we map these rotated layers back into the grid. The updated grid is 9, 5, 1, 2, 8, 11, 10, 3, 12, 6, 7, 4, 16, 15, 14, 13. This is our final result, which we return as the output. Here, we begin implementing the solution to cyclically rotate the grid. We define a class solution with a method rotateGrid, which takes the grid and the number of rotations, k, as inputs. Inside this method, we start by defining a helper function extract_layer to isolate a single layer of the grid. Each layer is essentially a collection of elements from the grid's boundaries, starting at a given depth, or layer index. To extract these elements, we traverse the top row of the layer from left to right, then the right column from top to bottom, followed by the bottom row from right to left, and finally the left column from bottom to top. This ensures that we capture all boundary elements of the layer in the correct order. The extracted elements are then returned as a list, which will allow us to manipulate them later for rotation. Now, we define another helper function, insert_layer, to place the rotated elements back into their correct positions in the grid. This function takes the grid, the layer index, and the elements to insert. We initialize an index variable, idx, to track the position in the elements list. Then, just as we extracted the elements, we insert the rotated values back in order. Starting with the top row, we update each cell one by one. Next, we move to the right column, inserting elements from top to bottom. After that, we handle the bottom row, filling it from right to left. Finally, we complete the left column, inserting elements from bottom to top. This ensures that the rotated elements are placed back in the correct positions, preserving the grid structure. After defining these helper functions, we calculate the number of layers in the grid by dividing the smaller dimension of the grid by 2, since each layer is essentially a ring within the grid. For each layer in the grid, we extract its elements using the extract_layer function. To handle the rotation, we calculate the effective number of rotations by taking k modulo the length of the layer's elements. This prevents unnecessary rotations by ensuring we only perform the minimum number needed. We then create the rotated version of the layer by slicing the elements list. The part after the rotation index is moved to the front, and the part before the index is appended to the end. Finally, we insert the rotated elements back into the grid using the insert_layer function. Once all layers have been processed, we return the modified grid as the result, completing the implementation of the solution. Here, we begin by defining the main method, rotateGrid, which will handle the cyclic rotation of the grid. The first step is to calculate the number of layers in the grid, which is determined by taking the smaller dimension of the grid, dividing it by 2. Each layer represents a single boundary of the grid that we will rotate. Inside the loop, for each layer, we first extract all the elements of that layer into a list using the extract_layer helper method. Once we have the elements, we calculate the number of positions to rotate by taking the modulus of k with the size of the layer. This ensures we don't perform unnecessary rotations. Next, we reorder the elements by splitting the list into 2 parts and rejoining them to reflect the rotation. Finally, the rotated elements are placed back into the grid using the insert_layer helper method. This process repeats for every layer, and at the end, the modified grid is returned. The extract_layer method is where we gather all the elements of a specific layer into a list. First, we initialize an empty list called elements to store the values. We then iterate over the 4 sides of the layer, starting with the top row. Using a for loop, we traverse from the left to the right of the top row and add each element to the list. Next, we move to the right column and iterate downward, adding elements from the top boundary to the bottom boundary of this column. For the bottom row, we traverse in reverse order, from right to left, appending each element to the list. Finally, we handle the left column by iterating upward, excluding the corners that were already processed. This systematic traversal ensures that all elements in the current layer are captured in the correct order, which is essential for the rotation logic. In the insert_layer method, we take the rotated list of elements and place them back into their respective positions within the grid. To do this, we initialize an index variable, idx, to track our position in the rotated list. Starting with the top row, we iterate from left to right, assigning each element from the list to the corresponding grid cell. Next, we move to the right column, filling it from top to bottom with the appropriate values. For the bottom row, we traverse from right to left, assigning values as we go. Finally, we handle the left column by iterating upward, filling in the remaining positions. This method ensures that the rotated elements are placed back into the grid in the correct order, effectively completing the rotation for the current layer. By repeating this process for all layers, the grid is fully transformed. To begin, we are given a 3x3 grid and the task is to rotate it cyclically by one step. First, we need to determine the number of layers in the grid. A layer is essentially a concentric ring of elements starting from the outermost edge. The number of layers in a grid is determined as the smaller of the number of rows or columns divided by 2. For this 3x3 grid, there is only one layer, which is the outermost layer. Next, we extract the elements of this layer. Starting with the top row, we take the elements 1, 2, 3. Then, from the right column, we add 6, 9. Moving to the bottom row in reverse order, we include 8, 7. Finally, from the left column in reverse, we add 4. Combining these, the layer's elements are 1, 2, 3, 6, 9, 8, 7, 4. Now that we have the elements of the layer, we rotate them. Since the rotation index k is 1, we calculate 1% 8, which equals 1. This means we rotate the layer's elements by one position to the right. The rotated sequence becomes 2, 3, 6, 9, 8, 7, 4, 1. Next, we insert these rotated elements back into their respective positions in the grid. The top row takes 2, 3, 6, the right column receives 9, 8, the bottom row in reverse order gets 7, 4, and the left column in reverse is filled with 1. After reconstructing the grid, the final output is 2, 3, 6, 1, 5, 9, 4, 7, 8. This completes the rotation for the first example. Now we can move on to a rectangular grid and multiple rotations. In this example, we are dealing with a 4x4 grid and rotating it by 2 steps. First, we determine the number of layers. With 4 rows and 4 columns, the number of layers is min, 4, 4, //2, which equals 2. The outermost elements form layer 0, while the inner elements form layer 1. Starting with layer 0, we extract its elements. The top row gives 1, 2, 3, 4, the right column adds 8, 12, 16, the bottom row in reverse order provides 15, 14, 13, 9, and the left column in reverse contributes 5. This yields 1, 2, 3, 4, 8, 12, 16, 15, 14, 13, 9, 5, for layer 0. Rotating this by 2% 12 equals 2, the new sequence becomes 3, 4, 8, 12, 16, 15, 14, 13, 9, 5, 1, 2. We then insert these back into their respective positions. The top row takes 3, 4, 8, 12, the right column gets 16, 15, the bottom row in reverse receives 14, 13, 9, 5, and the left column in reverse is filled with 1, 2. After completing layer 0, we move on to layer 1, which contains the inner elements. For layer 1, we extract 6, 7, 11, 10. Rotating these by 2% 4 equals 2, the sequence shifts to 11, 10, 6, 7. We then insert these back into their positions. The top part of layer 1 takes 11, 10, and the bottom part receives 6, 7. Finally, the updated grid becomes 3, 4, 8, 12, 1, 11, 10, 16, 2, 6, 7, 15, 14, 13, 9, 5. This concludes the processing of the rectangular grid with 2 layers and 2 rotations. Next, we consider a simpler case, a single row grid. In this final example, we have a single row grid with 5 columns, and we are asked to rotate it by 3 steps. When determining the number of layers, we calculate min, 1, 5, //2, which equals 0. This means there are no layers to process in this grid. As a result, the grid remains unchanged. The output is simply 1, 2, 3, 4, 5. This scenario highlights that single row or single column grids do not require any layer-based rotation, as there are no concentric rings to manipulate. To understand the time complexity of this solution, we can break it down into 3 main operations: extracting a layer, rotating the layer, and reinserting the layer. First, when we extract a layer, the function iterates over all the elements in the layer. For a given layer I, the number of elements to process is determined by the perimeter of that layer. This can be calculated as 2 asterisk, rows plus cols, 4 asterisk I, 4. This formula accounts for the top row, the bottom row, and the 2 vertical sides of the layer, adjusting for overlapping corners. Next, rotating the layer involves slicing and concatenating the list of elements in the layer, which takes linear time proportional to the number of elements, or O(m), where m is the size of the layer. Finally, reinserting the layer back into the grid also requires iterating over all the layer elements, which again takes O(m) time. These three steps form the core building blocks of our algorithm, and each is performed for every layer in the grid. Now, if we think about the grid as a whole, the total number of layers is determined by the smaller dimension of the grid, specifically number_layers equals min, rows, cols, //2. For the outermost layer, the cost of processing is proportional to the grid's perimeter, or O, rows plus cols. For inner layers, the cost decreases because each layer has fewer elements. For instance, the second layer requires O, rows plus cols 8 operations, as the effective dimensions shrink by 4 for each step inward. Summing up the costs across all layers, we find that the total time complexity is proportional to the total number of elements in the grid, or O, rows * cols. For a square grid of size n×n, this simplifies to O(n²). In terms of space complexity, the algorithm uses temporary storage to hold the elements of each layer during extraction and rotation. The largest layer, which is the outermost one, determines the maximum auxiliary space required, which is proportional to the grid's perimeter, or O, rows plus cols. Since the grid is modified in place, no additional space is used for the grid itself, meaning the overall space complexity is O, rows plus cols, or O(n), for a square grid. Let's compare this solution to a naive approach. A brute force method would involve rotating the entire grid k times, where each rotation requires shifting all grid elements. This would result in a time complexity of O, k * rows * cols, making it highly inefficient for large values of k. In contrast, the optimized solution reduces k modulo the number of elements in each layer, ensuring that no redundant rotations are performed. By focusing on layer-wise rotation, the time complexity is reduced to O, rows * cols, which scales linearly with the grid size. When we analyze the best, average, and worst cases, they all share the same time complexity of O, rows * cols, because the operations depend solely on the grid's dimensions, not on the actual values or distribution of the elements. Mathematically, the total number of grid elements is rows * cols, and each element is processed in constant time during extraction, rotation, and reinsertion. This confirms the overall time complexity is O, rows * cols. For space, the largest contribution comes from the perimeter of the largest layer, which is O, rows plus cols. Other auxiliary variables only require constant space, reinforcing the space complexity as O, rows plus cols. Now, let's discuss some common mistakes that you might encounter while solving the problem of cyclically rotating a grid. One frequent issue is incorrect indexing when determining the start and end positions of each layer. Since grids can have varying dimensions, these indices need to be calculated dynamically, otherwise, you risk out-of-bounds errors or improper rotations. Another mistake is treating the entire matrix as a single unit and rotating it as such, rather than addressing each layer individually. Remember, each layer has its own rotation pattern, and mixing them up leads to incorrect results. Additionally, failing to account for modular arithmetic when rotating by k positions is another pitfall. Without applying k modulo the layer's length, unnecessary computations occur, and the rotation might not be accurate for large k values. Edge cases are important too. Grids like 1x1, 1xn, or those with just one layer can behave differently. Ignoring these scenarios could lead to runtime errors or unexpected outcomes. Finally, inefficient copying of elements using nested loops can slow down the solution significantly. A better approach is to flatten the layer into a one-dimensional array for simpler and faster processing. Keeping these points in mind will help you avoid common stumbling blocks. Now let's focus on insights that are particularly useful during interviews. First, pattern recognition is key. Many grid problems require you to break the grid into smaller, more manageable subproblems, like isolating and processing individual layers here. Interviewers want to see how effectively you can decompose the problem and identify such patterns. Another critical aspect is the trade-off between time and space efficiency. For example, in-place rotations save space but are more complex to implement, while flattening layers is easier but involves extra memory. Be prepared to explain why you chose a particular approach and how it balances these trade-offs. Additionally, handling edge cases explicitly, like empty grids, single layers, or non-square matrices, is something interviewers value because it shows thoroughness and attention to detail. Clear communication is also essential. Walk through how you extract elements from a layer, rotate them, and reinsert them back into the grid. Using diagrams or examples to illustrate your thought process can make a big difference. Finally, this problem connects to other similar ones, like rotating a square matrix 90 degrees clockwise in LeetCode 48, traversing a matrix in spiral order in LeetCode 54, or generating a spiral matrix in LeetCode 59. Drawing on these related problems can help enhance your understanding and showcase versatility. Let's explore a few alternative approaches and their trade-offs. One option is in-place rotation, which minimizes space usage by not requiring additional data structures. However, this method is more complex to implement because it involves managing indices carefully to avoid overwriting values prematurely. A second approach is the flatten transform rebuild technique. Here, you extract each layer as a one-dimensional array, perform the rotation, and reinsert it back into the grid. This method is conceptually simpler and easier to debug but requires extra space for the temporary arrays. A third option is recursive layer rotation, where you first rotate the outermost layer and then recursively process the inner layers. While this approach can be elegant, it risks stack overflow for larger matrices and can be harder to manage in practice. In terms of trade-offs, flattening layers generally involves an O(n)² time complexity for extraction and reinsertion, while the actual rotation is O(k). On the other hand, in-place rotations aim to eliminate the O(n)² overhead but come at the cost of higher implementation complexity. For space complexity, in-place solutions use only O(1) additional space, while methods like flatten transform rebuild require extra memory for the intermediate arrays. Balancing these trade-offs depends on the specific constraints of the problem and the priorities of your solution. Great work! To recap, we solved the problem by focusing on layer extraction, rotation, and reconstruction. This approach is efficient and adaptable for similar problems. Thank you for joining. Be sure to like, share, and subscribe for more problem-solving insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!